Hello and welcome to Today I Learned Climate, the show where you learn about climate change from scientists and experts. I'm Laur Hesse Fisher from the MIT Environmental Solutions Initiative, recording from my home due to the coronavirus pandemic. If you're listening to this while self-isolating, be well to yourself and to others during this tough time. You are joining our Energy and Climate series, which we're running in collaboration with the MIT Energy Initiative. We're now going to start digging into what will it take to generate the electricity our society needs without generating carbon emissions. For the rest of this season, we are going to be exploring our clean energy options: wind, solar, storage, nuclear power, and others, and the benefits and drawbacks that come with each of these technologies. It might not be a surprise that we're kicking it off with a conversation about wind and solar power. And to do this, we spoke with Dr. Magdalena Klemun.
My name is Magdalena Klemun, and I'm a postdoc at the Institute for Data Systems and Society here at MIT. I'm interested in the fundamental mechanisms of innovation and how they affect different clean energy technologies and lead to improvement over time.
And wind and solar have improved a lot in the last few decades, but we will get to that in a minute. Wind power and solar power are very different kinds of energy sources than coal, oil, natural gas, and even nuclear power. First, they are renewable.
Instead of burning a fuel that contains carbon, renewable technologies convert either the kinetic energy in air or in water, in the case of wind and hydro, into electricity, or they convert light into electricity. That would be photovoltaics.
Photovoltaics are probably what you think of when you hear about solar energy. These are the bluish panels that you might have seen on roofs of buildings or in big rows on land. Sunlight is absorbed by the solar panel, which causes a process that dislodges electrons and creates an electric charge. As we've covered in a previous episode, fossil fuels like coal, oil, and natural gas are burned to create steam and turn a turbine. Wind and hydropower also involve turning a turbine, but they do so using the force of the wind or flowing water. So that means you don't need to burn anything to turn the turbine and generate electricity.
And since we live in a world where what we're really trying to get rid of is carbon, that's a pretty convincing proposition.
Wind and solar power are appealing ways to generate electricity for a lot of other reasons, too.
The economics are different across locations, but every single country on this planet has direct access to solar and wind energy. And so that's pretty unique for an energy source if you consider, for example, that 70% of global resources of natural gas are concentrated in 5 countries. And then another reason is that renewable energy technologies have proven easy to scale. So all we need to do to build a megawatt scale solar photovoltaic plant instead of a small rooftop system is to put more solar panels in a row and more rows next to each other. So in other words, we scale by repetition, and that's relatively easy.
This is relative to coal, natural gas, and nuclear power plants, which require a lot of infrastructure to build.
And in addition to that, renewables are abundant in the sense that there's enough wind and sunlight and kinetic energy to supply all of our electricity needs.
Right. Our planet has no lack of wind or sunlight, and there's no fear that we're going to run out anytime soon. In 2019, renewable energy generated about 18%, that's 18%, of our electricity in the United States. In fact, in just this past year, wind power actually overtook hydropower as the U.S.'s top renewable energy source. And in some states, like Kansas, Iowa, and Oklahoma, over a third of the electricity that state produces comes from wind power alone.
Looking back in time, both solar photovoltaics and wind have grown rapidly, actually faster than expected by many international organizations and also by academic researchers. Wind and solar capacity have doubled approximately every 3 years over the past 30 years. So that's a significant growth trajectory. And that growth has been driven by a couple of interrelated factors. In the 1960s and 1970s, a lot of investment and policy support in renewables was driven by concerns about energy security. Particularly in the area of fossil fuels, the US relied heavily on imports from other countries. And then over time, these policies supported significant investments in research and development to, for instance, increase the efficiency of solar panels. And that made the technology better. It also made it more reliable and cheaper. At a high level, most renewable energy sources are competitive or cheaper than fossil generation across different locations. And solar photovoltaics is also increasingly cost competitive. So a solar panel now costs about 1% of what it cost in 1980. And that's a really significant change.
All of this is sounding like really good news for wind and solar power. But there's a catch.
Wind and solar electricity are available when the wind blows and when the sun shines. But that's sometimes, but not always, when consumers demand energy.
This is a huge difference from fossil fuels and also from nuclear energy. As long as we have the oil, natural gas, uranium, we can use it pretty much whenever we want to generate electricity. But we can't always produce electricity from wind turbines and solar panels. Remember how in episode 1, Harvey Michaels spoke about how the electric grid needs to always be in balance? Here's a clip from that episode.
The complexity of the grid is that there needs to be exactly the right amount of power put into the wires to serve all the instantaneous needs of all the people on the system. It doesn't really have the ability to store electricity in the wires themselves.
That means that if you want lights at night, having solar power during the day doesn't help you. Same with when the wind's not blowing. There are ways to help with this problem.
The term energy storage refers to a class of technologies that capture energy available at one point in time to make it available at another point in time.
To give a few examples, there are large-scale batteries, like the lithium-ion batteries that are in electric cars. Another is something called pumped hydropower, which creates a flow of water when we need it.
Pumped hydro essentially means that when we have excess electricity in the grid, we use this electricity to pump water up on a mountain, and then we release it through a turbine and a generator to generate electricity when prices are high and we want to make money.
The thing is, all this energy storage costs money. And when you factor in the cost of these storage technologies, that adds to the cost of wind and solar power.
For each unit of electricity generated by a wind turbine or by a solar panel, you also need to factor in the cost of the amount of storage that you need to make sure the electricity is available on demand. And when we do that, renewables are cost competitive only in some locations and for some storage technologies.
So a big question is, will energy storage become cheap enough for wind and solar to provide most of our electricity? And if so, when? Well, it turns out that this could be possible more quickly if we bring in some other technologies as well.
In absence of significant breakthroughs that can reduce the cost of energy storage, and these breakthroughs might very well happen, but in absence of these breakthroughs, a good pathway is one where both wind and solar grow significantly, and storage does as well, but then we also expand transmission infrastructure, and we invest in demand-side management, so we don't expect energy storage to do 100% of the job.
Demand-side management means we change the demand for electricity, so when we use it and how much of it we use. So in this scenario, Dr. Klemun is saying that if our electric grid could more easily move electricity across locations or shift it over time, that could partially replace the need for energy storage, because these things also help smooth out the variability of wind and solar.
Renewable electricity costs with storage would be half as expensive if we use these other technologies to meet demand during the hours where wind and solar aren't available.
There's another way to provide clean electricity on demand.
If you look at the scenarios that allow us to stabilize CO2 concentrations in the atmosphere, most of these scenarios actually assume that there is a mix of wind and solar as well as other clean technologies, such as nuclear and fossil generation with carbon capture and sequestration, if we can commercialize it.
Real quickly, carbon capture is when you burn fossil fuels, but capture and permanently store the CO2 before it enters the atmosphere. As Dr. Klemun just said, carbon capture isn't commercially viable yet. There's still a lot of research and market development that's needed for carbon capture to be adopted at a large scale.
Technologies like nuclear and fossil generation with carbon capture and sequestration can supply energy on demand. By keeping these technologies in the mix, we at least keep the option alive to use these technologies rather than artificially constraining our options. It's like you're putting a lot of really important eggs in very few baskets.
This is why we're going to spend the next several episodes looking at these technologies. We'll cover energy efficiency and how it can help us in the clean energy transition, and we'll dig into nuclear power, carbon capture and storage, and even fusion energy. And if you're interested in learning more about renewable energy, then you're in luck. The MIT Energy Initiative has a bunch of episodes that explore batteries and storage, solar power, and how the cost of energy technologies change over time. Google MIT Energy Podcast or check out the links in our show notes. We'll also include links to Dr. Klemun's own research at the group that she works with, the Transic Lab at MIT. Feel free, as always, to send us your questions over email, tilclimate@mit.edu, or on Twitter @tilclimate. Thank you to Dr. Magdalena Klemun for speaking with us, and as always, thank you for listening.